Hello. Let's see if we are live now. Okay, we are live. So today we are going to deal with this question paper. So this is the question paper that we are going to deal with. But the principles that we are going to be following is answering long questions. Long questions in electric circuits. These questions deal with what will the adding and removing of a resistors in parallel or circuit or series affect the reading across an ammeter, the reading across the voltage. This question comes in different ways. You might find that in another ways the same question is asked to say that what will happen to the reading across an ammeter or a voltage if a resistor burns out, or maybe if a switch is open and closed. But what you must know is that absolutely or ultimately these questions are the same. So we are going to deal with what happens with the adding and removing, and what will happen to the current across a certain resistor. So now we are going to start with this 20 which is the 2023 question paper. Let's go down in order to start answering this question paper. So it says that the circuit diagram below shows a battery with an EMF of 12 volts and internal resistance of 0.5 ohms connected to three resistors, and says that a light bulb, a switch, and an ammeter connecting wires. The ammeter and connecting wires have negligible resistance. Okay, let me set up so that I'm able to see the live chat, so that I'm able to interact with anyone who wants to ask question in the chat. So there we are now. So it says the first question, or the question that we are going to focus more and highlight more on, is this question here. This is the question that we are going to highlight more, which is 8.3. So now it says that switch S is opened. This is the switch S which is opened. And then another thing that we get here, it also said that now what will happen to the brightness of this bulb. So we are opening and closing this switch, and then they will say what will happen to the brightness of this bulb. So we are going to use the very same principle, but before we go to the very same principle, we are going to first answer the questions in between. I'll try to make timestamps so that you can move forward to solving long questions of electric circuit. So now the first question, it says that state Ohm's law in words. It states that the potential difference across a conductor is directly proportional to the current passing through that conductor, and then it says that provided the temperature remains constant. So that's our Ohm's law, which is derived from this, which is V equals to I times R, where we know that because in this resistance is constant, when the current increase, the voltmeter also increase, and then vice versa. When this one decrease, the other one will also decrease. So that's what we know, and that's how we apply it there. And then when we continue, it says that the total external resistance of the circuit. Now, when you go to the total external resistance of the circuit, you have to know how to group resistors. You have to know how to group resistors. It's very much important when it comes to here. So now, how do we group these resistors? So now, when it comes to grouping the resistor, we have to first see that how many branches do we have. We have two branches, this branch and this branch, but this branch is further divided into what? This branch is further divided into two more branches. So you have to know how to group branches. So first you have to know that all these resistors, let me circle them for you, or let me highlight them for you. All these resistors here, they are in one branch. All these resistors are in one branch. So if all these resistors are in one branch here, the important thing I want us to learn from that is that now we can add the total resistance of these branches and the total resistance of these branches, and then we use the formula of Rp equals to R1 times R2 over R1 plus R2. So we are going to first find this. We put it as R1, and then what we'll put towards our R2 is that one. That's how we are going to do it. You must first learn how to group these resistors, but nevertheless you must know you use this very same formula for this whole branch, or also use this very same formula for these two branches as they are parallel to one another. If you add resistors that are parallel to one another, you use this formula. But if they are series in regards to one another, use this formula. First, let's fight for this to be a one resistor. Let's find the total resistance across this combination. So if you want to find the total resistance across this combination, we'll just come and say, let me move this it's gonna, okay, let me move this side. Yes, and then let's do Rp equals to R1 plus R2, or times R2 over R1 plus R2. And then we come this side, and then when we come this side, we're just going to substitute this 10 times 10 over 10 plus 10. So this is gonna be 100 over 20 is just gonna give us 5. This is 5 ohms. So the equivalent resistance of these resistors, let me highlight them for you. Equivalent resistance of these resistors in green is gonna give us 5 ohms. It's gonna give us 5 ohms. Now let's add this total of this resistance with this. So we are going to add them in the straight line. So because we have found the total resistance of this one of 5 ohms, now we are going to find the total resistance when we add with the bulb, this bulb, which is what, 10 ohms. So this is the branch on top. The branch at the bottom is going to be like this. I'm drawing it like this so that I want us to know how we are simplifying. We are simplifying all this. So now, if you check here, you'll find out that because this one, we have found it to be a total of 10 through this calculation, it will tell us that now we have resolved it to find 5 here. We resolved it to find the 5 that we found here. So this is 5 represent these two. So now because we can clearly see that no, this 5, which is the total resistance across this combination, when we relate it to this, it's in series. So you're just going to add them in a straight line now. It's just going to be 5 plus 10. So it's going to be R equals to 5 plus 10. The formula that we're going to use is that R total equals to R1 plus R2. Then it's just going to be give us 15 ohms. So there's our 15 ohms across this branch. This branch is 15 ohms. And then this branch is what? It's also 15 ohms. So now because this 15 ohms, how do we get our total resistance? We come back to this formula of calculating the what? We'll come back to this formula. Let me show us the formula. This very same formula. Now we are substituting. Now let me change the color. So now let's use this very same formula of Rp equals to R1 times R2 over R1 plus R2. So now we have resolved the total resistance of this branch, which is now 15 ohms, which is this one, which give us 5 plus this 10 is 15. So the total of this branch is 15. The total of this branch is 15. So now we can add. If they say how does our circuit look when there are those total resistance that we just did there, that will be our 15 there. That will also be our 15 there. We must learn to combine the resistors. That's very much important. Now we have combined them, so we are left with this. This is ultimately this, because if we add all this on top, you get 15. And then you just say 15 times 15 over 15 plus 15. And then now you'll just come and add here. And then it just gives you half. If they're the same, it gives you half. If resistors are the same, let me just confirm. 15 times 15 over 15 plus 15. So it just gives you half is 7.5 ohms. So we have got it to be 7.5 ohms. And then now, let me just wrap all these so that we can work. Let me just wrap all these. Let me wrap this one. This wrapping takes time. Let me wrap like this. Oh, I also included the 7.5, but I know it. Okay, I'll write it again. So let's wrap also this. If you have any questions, you can bring in. If you understand, you can give the video a thumbs up, or maybe comment that you understand. Now let's go to the following question. Here we had gotten 7.5 here, so that I'm writing it down because in physics they're tricky. Sometimes they might say that you have to use this amount. And then let's continue. It says that the reading on the ammeter. So this is the reading on the ammeter. So now, when it comes to the reading of the ammeter, you must first ask yourself to say, what do you have? What do you have now in relation of calculating the reading of the ammeter? So let's see the information that we have. This is the total external resistance. Ne? This is the total external resistance. And then we also have the internal resistance, and we also have the EMF. So what is our main formulas? That's why always I keep the formula sheet down here, so that we always know at the formula sheet which equation are we going to use. So now this is the big equation, which is EMF equals to I R plus R. And then in this big equation, what do we have? External resistance, we calculated it. The internal resistance, we have it. EMF, we have it. That means we are left with current, with which they want us to calculate, which means that now you just come and substitute there. So now let's just substitute. Let's just substitute this to this equation, equals to EMF equals to IR plus R. And then now you come here, we put 12, we leave our current like this. I'm writing it like this so that we can distinguish between it and 1. So, and then 7.5 plus 0.5, and then now our current is going to be also, I just did this, just gonna be, it's 7.5 plus 0.5 is gonna be 8, but let me just write it for the sake of it. It's gonna be 8 underneath, so that's gonna be 12 over 8. 12 divided by 8 is how much? 1.5 amperes. 1.5 amperes. So this is 1.5 amperes here. 1.5 amperes. There is our answer there. So let me also write it here. 1.5 amperes. Then when we continue, it says that the power dissipated by the resistor R3. This is the resistor at R3. What is power? There are many equations of calculating power. Power equals to I squared R. Power equals to V squared over R. Power equals to VI. This one is the most simple one. Power equals to the rate at which work is done. But yeah, it just depends on the equation that we are given. Just depend on the equation that you are given, or the information that we are given. So let's check the information there. Which information can help us with calculation power here? Dissipated power across the which resistors R3. So now we have its resistance. So it's easier to use this or one of this equation. So what do we need now? We have its resistance, but what are we left with? We are left with maybe current or voltage, current passing through here, or the voltage passing through here. But I think what will be easier is voltage, because why? Finding voltage will be easier because the voltage from the battery dissipated around the parallel branches is the same. They dissipate the same voltage. So now it means that if we find the the V external will be the voltage across this one. So now let's find our V external. How are we going to find our V external? We have our V internal. So we have our V internal. We don't have it, but we can calculate it. I'll show you how. So EMF is made of two things. EMF is made of V internal plus V external. So it's just that formula that we were using here of saying R equals to R plus R. And then we just say the I multiply that, multiply this. And then this is our V external. V internal, this is our V external. So that's just what our EMF is made of. So now when we are realizing that this is what we make our EMS, how will we find our V internal? We need to first find our EMF, and our V internal will then find our V external. So now in this, yeah, somebody's calling me. I will get to them. So in this, how are we going to find our, in all this, how are we going to find our V external? So we are just going to find our V internal, remove it from the EMF and find it there. So our V internal equals to IR. It's just this current, V equals to IR. And then it will come to say what? It will come to say, now in this, we are going to add our current there. Our current, which is 1.5. And then our resistance, which is 0.5. And then now we come and multiply 1.5 multiply by 0.5. It's just gonna give us 0.75. It's gonna give us 0.75, and then that is our V internal. So how do we find our V external? We just remove it from EMF to just say make this subject to the formula EMF minus V external. It will be EMF minus V internal. So let's take it from the EMF V external. So is our EMF 12 minus 0.575, then it's going to give us 11.25 volts. So that's our V external. It's going to be the voltage used here. The power is going to be the voltage used here and the voltage used here, and it's the voltage that is going to be the same because it's parallel. Voltage in parallel is the same, which will make us here to therefore come and conclude that what this voltage across this resistor is also 11.5. But note that in this branch, this voltage is going to be shared by this resistor until it comes to be divided by those two resistors. Now let's just come and say power equals to what? Power equals to the one with a voltage and the one with resistance, 11.25. And then that 11.25 we square it, and then we used also the resistor, which is 15. Then it's 11.25 into 11.25 squared into 15 multiplied by 15. How much does it give us? It gives us a lot of power, this one. 1998.44 watts. So that's the power dissipated now. So now let's continue with the questions. Now when we continue with the questions, it continues to say that the question that we came here for, and then let me just write this answer here of saying 19.8844 watts. So now let's continue. It says that switch S is open. We open this switch. So let's open the switch there. Let me wrap here so that we work. When we wrap here, we'll find out that now Okay, when we wrap here, we are also gonna find out that now this switch is this one is not working, because what they say, this switch is open now. It's open like this. This one is not working, meaning that it's gonna alter the current passing through here. So now the question is, if now this switch is open, and then this it means that indirectly they are saying that they are removing this resistor. So because they've removed that resistor, they're saying that what will happen to the brightness of that bulb. So just know that the brightness is directly proportional to the power. If the power increase, we use the power to determine the brightness of an item. That's what we use. We use the power to determine the brightness. So now it's a way of calculating the power. If like you don't trust your answer well, you can calculate the power, and then you therefore conclude that now the brightness has changed. So let me wrap this. So now you can calculate the power before and after and show them now that this is what happened now. Here they didn't say you don't use calculation, so you can definitely use calculation to explain in 8.3.1. So in 8.3.2. So now other one says without using calculation, but here they didn't specify, meaning that you can use calculation, choose whether to use calculation or not. I'm trying to I was checking the chat if there is any question there in the chat. So now let's continue and go straight to this. I hope okay, just the cable. And then it says that increase, decrease, or stay the same. We don't know yet. We have to conclude. We are concluding with the reason. It's funny that they want you the answer on the top, and then they say that what will happen with the brightness. We first come in first reason, and then the reason will conclude for us. Will conclude for us to say that, oh, it's increase, it decrease. So the reason will conclude for us. Explain the answer of saying 8.3.1. So now when we go to our diagram there, 8.3.1, it says that what will happen to this brightness. So the first thing is that the principle that guides all this, what will happen to the brightness of this bulb if this switch is open, meaning that we have removed resistors in parallel. The principle that guides is that when we remove resistors in parallel, total resistance increase. Total external resistance increase. When we remove, vice versa, when we add resistors in parallel, total resistance does what? Decrease. So you can even understand it maybe by this simple circuit. Let me draw a simple circuit for us to understand and grasp that, because they are like inverse, adding and removing, and the total resistance. So let's say this one is 3 ohms, this one is 3 ohms. Now if we find the total equivalent resistance of this, it will be a 1,5 ohms, using that formula of Rp equals to R1 times R2 over R1 plus R2. Why? How did I find it? I just it's half. If we use the same number, it gives you half. So now if this is the total equivalent resistance across the parallel, if we remove this resistor, the total resistance is going to increase, because now we'll be left with only this 3 ohms. And then what it will be, the R total, Rp or R total will just be 3 ohms. And then what is R here? The R is 1.5. So you see that we removed, but the total resistance did what? The total resistance increased. So it's like the inverse of one another. So that's the guiding principle. When we remove the resistors in parallel, total R total decrease. We removed it increases. We say they are inverse. R total will do what? Will increase, because we have removed. R total will increase. That's the first step. We haven't concluded 8.3.1. We are going to use the reasoning to go back. So, and then you continue with your reasoning to say that if always the R total increase, therefore the current of the circuit decreases. That's the current. Why? Is because current is inversely proportional to what? To resistance. We are still reasoning there. We are still reasoning. And then now, wait, because current has decreased, you also have to say how that affect the voltage, the V lost and the V internal, because there's V lost, there's V internal. So now, if you look at the equation for V lost and and also V internal or V lost here, we can also say V internal plus V external. So now this is going to be equivalent to I. This is going to be equivalent to IR. It's going to be equivalent to IR. And then this is going to be equivalent with what? This is going to be equivalent with this is going to be equivalent with IR, the capital letter R, R external, R internal. So now, before the voltage goes outside, it's taken by what? It's taken by the V internal. Before the voltage it goes outside. So the V internal is the boss, because you can't it takes the voltage and there's nothing you can do about it. So it's like the boss, because it's the one that determines the V external. It's the one that determines the V external because it takes first. So first, before the V external goes, it takes the voltage. It's like the power dissipated in the voltage dissipated, or the voltage used in the battery before it goes out. So now let's get back to this equation. So it's going to take first from the EMF. EMF is constant, and then EMF is constant. EMF is constant. Is constant. It's very much important point, because it's the one that if it was changing, it wouldn't be like this. But now, because let's see what will happen to the V lost. V lost equals to IR, and we had that the current decreased, and then the V equals to IR. It means that if the current decreases, the voltage will also decrease. The current decreases, the voltage will also decrease. We're talking about V lost because this R is constant. This internal resistance is constant. Therefore, now this one will also increase. So now you'll say V lost will decrease. And then you can also mention a reason. They will just come and choose what they want to mark here, because you may find that now in the memo there are marks for different things. So then you say R is constant. I'll show you the most important points, but now you are building here. We are getting to the brightness of the bulb here. So now when we continue here, if this one has decreased, it means now therefore V external will increase, because less voltage will be spent inside the battery. It means that there will be more outside. So like how a less number will be subtracted from the EMF, there will be more outside. So now you just come and say V external, that's what V external is going to increase. So this is going to be your determining factor. This is going to be your determining factor of saying that what is power? Power equals to V squared R. Therefore, let's check. If this has increased, this will also increase. Therefore, you'll say brightness is power. That's why when you buy light bulbs, they'll be written 50 watts, 100 watts. And the greater the watts, the greater it lights up. So that's also what you have to keep in mind. Brightness is power, or directly proportional to power. You'll say brightness is what? Brightness, you can write it in many ways, is directly proportional to power. And then you continue to say that, therefore, power increase. You write an equation power equals to V squared R. The how someone will be asking, how about those other equations of power? What do we make of them? So there's also this power equals to I squared R, this one. So this one needs you to first see this current. Note that, let me show you, because some students make the mistake here. They make the mistake here. Let me show you where some students make the mistake. They make the mistake here to say, now, if the current decreases now, they will come and say, oh, because the current has decreased here, it means that current has decreased, therefore power decreased. No, 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 no. What is this current? This current here that we see up here, the current that we see is the current, the total current, not the current across this bulb, is the total current. That's why we are not supposed to conclude from here, from this step of saying that because now total resistance has increased after removing a resistance in parallel, now because the total current has decreased, therefore it will lead to this equation saying current decreases, power will also decrease. So that's not how we do it, because this is measures the total current here. If they had said that what will happen to the reading of A1 if this happened, you could end your answer here. You could end your answer here, and then you'll get your marks. You'll get your marks. But now, what will happen to the current across this? That's how we can use this equation if we solve the current across this. So now, if you check this, now first current was divided. It goes to this branch and it goes to this branch. But now, if this branch is removed, we'll see that no, this one will end up getting total current. It will end up getting more current than it was getting before. Therefore, because the more current has increased, this one will also increase. But we don't use this, which measures the total. Actually, you must say total here. You must say total. That's why I said R total. R total and I total. So you must know where to end. But if they were saying this one, you could be correct, because this is the total of or across this one. So that distinction is very much important, because if they had also seen what will happen to the voltmeter over here, to the voltmeter reading, if this one is removed, you will end your answer here. You will end your answer here to then say, this is my answer. You say V external will increase because the voltage across this will measure the V external. So you have to know how to differentiate. So you see now I've helped us to understand the ammeter reading, or the variables of this one, and the voltage variables of the total circuit. So you must know how to differentiate. Is very much important. And then now it means that because we have gotten our answer to say brightness increase. So the answer is what? 8.3.1 increase. So this, the funny thing is that this is the paper that I wrote. I wrote this paper in metric. So I remember when we got out of the exam, where I was arguing with this guy. It's increased. And then he said, how do you know? I said, we used this reasoning. And then I remember after writing, because I still had time, I finished early, I went back and calculated the power before and the power after, and then I just confirmed what I had written. So you can also do this if some say without the use of calculation, but this one there's not that restriction. So you can choose whether you want to use calculation and choose whether you don't want to use calculations. So if you have any questions, you can come in. If you don't have any questions, it's fine. So now let's just continue now. So now we are going to answer this question. Now when we continue with this question, it says as follows. In the circuit diagram below, the battery has an EMF of 24 volts and internal resistance of 0.3 ohms. The light bulb L has a resistance of 9.5, and R, that resistance R, and of unknown resistor. And then it says that ignore the effects, the resistance of the ammeter. Okay, wait a little bit. There's someone in the room. Just a few seconds. So, okay, now let's just continue. It was a small distraction. So now it says that state Ohm's law in words. Ohm's law is that the potential difference across a conductor is directly proportional to the current passing through that conductor, provided the temperature remains constant. So as I said back there, is according to this equation there, that's the one that we use. And then it says that both switches S1 and S2 are closed. The reading on the ammeter is 0.8 amperes. So there it is. Sorry. And then it says that calculate the current through the bulb L. Sorry, the current through the bulb L. So you must check what are you given here. We're given this internal resistance, and also we are given this 9.5. What else? We are also given the ammeter reading. This ammeter reading, 0.8. So we are not given this, but we are looking to find the ammeter reading through bulb L. So now we have to know how can we use the information that we're given in order to come up with the answer. So now, in order to find the current equals to V over R, we have this resistance. The resistance that we have here is the resistance of what? We have the resistance of a 9.5. But now what don't we have? We don't have the voltage across this. But we must know that the voltage across each branch here, let me just show you. This is the voltage across this each branch here is the same. Each branch is the same. They are trying to trick us. The current is across all these branches is the same. That's what a student should find. It only won't be the same if there was a resistor here, but now there is no resistor there. It's going to be the same. It's going to be the same all because all these three resistors are parallel in relation to one another. This one, except this one. So now, because the voltage is the same, we can use the voltage of this branch to find the voltage of this branch. How do we find the voltage of that branch? V equals to IR. And then we just come and say, what is our current then? Our current is, we are given over this, it's 0.8. And then now, what is that resistance of that one here? Is 13. Just come and substitute to say that 13, 13, let me check. It says that 13 times 0.8 is 10.4. 10.4. False. Let me check the live interaction. If okay, there's no question yet. So now let's just write is it our final answer? It's not our final answer. You just come and substitute here. I had lost my train of thought. So our idea was to find the voltage across this, and it will be the same because voltage parallel is the same. And then we just come and divide to say that, okay, 10.4 divided by what? Divided by 9.5. Okay, there it is. Answer 9.5. Okay, our current is gonna be 1,09 amperes. So this is gonna be have 1,09 amperes. There it is. 1,09 amperes. So now let's continue. the reading on A2. Where is A2 here? It's here. So now, how do we find the reading of A2? The easy way to find it is because now we have the current passing through this branch, current passing through this branch. So this branch is 1,09. Current passing through this branch is 0.8. Current passing through this branch is gonna be what? We solve it and then we just add this plus this, and then it's gonna be the total. So now let's find the current passing through this branch the same way. We find it the same way. We just the voltage that we have 10,4, which is the voltage over this parallel. Let me let me just go back so that I can find the answer of the volt. I want to confirm if this is correct. I've opened the live in another device, so I think it will allow me to go back and then just to confirm. If you see just rubbing before you finish, it will give you a problem. It's just 10.4. There it is. Okay, now when we continue, or we just come and say just as how we did it there, we just come and say that now what is our current? What is our current equals to V over R? Then we come and say, okay, now how do we plug that into the equation? We come and plug that in equation to say 10.4 over R. Our R is what? Is 9. Then you come and say 10.4 over R. What is our R again? Our R is the 9. And then it says 1.15, 1.15 amperes. So this is going to be 1.15 amperes. And then we just come in, not amperes, not ohms. So now we just come and add all that. So it's 1.16 technically, because I can round it up. 1.09 plus 0.8 plus 1.16. There is it's just gonna be 3.05 amperes. So here's our reading, 3.05 amperes. Now the resistor R, the resistance of resistor R. Sorry. Now let me just wrap all these. So this one has a lot of marks, meaning that we are going to exercise our brains. So now let me wrap this. Now it says that the resistance R. So now let's check in this equation. Now this is always our go-to equation. So we can just substitute in this equation. We can just substitute to say that, okay, we have our EMF here, which is 12. Okay, I'm sure you're still with me. And then we have our current, our total current, which is 3.05. I hope you're still with me. And then now we have our R is the one that we don't have. I'll tell you more about this R, because it's the one which is the R external now. And then here our V internal is the R internal is this. And then now this is where the danger lies. So in R here, R equals to R series plus R parallel. What do I mean by that? I mean this R and also all this R. This one, this R, all this is the R parallel. This one is the R series. Meaning that if we solve this, we can solve for the R external. But if we solve it, we come and substitute here. And then this here we can solve it because it's just all these the resistors connected in parallel to one another. And then we solve for the RS. Our RS is the R they are looking for. So we start here, we substitute these two, we solve the RS. There it is. Now let's first solve here. So now it's gonna be 12 equals to 3.05 into R external plus 0.3. So a way that we do it, you just come and divide both sides by 3.05, divide by 3.05, this divided by this, and then that side we just keep it the same, and then it will be R external. We take this that side, so it's gonna be 12 over 3 over 0.5 minus 0.3. That will be our R external. So I hope I didn't lose anyone. 12 over 3.05 minus 0.5. So it's just gonna be 3.43. But no, let's not round because this is not the final answer. I'm just writing it like this, but in the calculator I'm just gonna keep it like this, and then I'll just say answer, so that you don't round, because if you round sometimes you find that the answer that you get is off. It's not off, but it's like it gives you around decimal points which are wrong, sometimes even whole numbers which are wrong. So now when you just continue, you just come and substitute here. That is our this. But no, let's first find our R parallel. R parallel is just this, and this, and this. And then we just come and say, okay, R1 1 over R total equals to 1 over R1 plus 1 over R2 plus 1 over R3. Then we just come and do this, solve here, and then the one on the top was 9, 1 over, I have to let me start up there because I have to equate 1 over R total equals to 1 over 9 plus 1 over 9.5. Which one else is there? Is 13. Is 13 plus 1 over 13. So now you just come and add this one in a straight line. Just press the calculator this side. Let me press the calculator very fast. Plus 1 over 13. There is our 13 there. So it's not giving me, here is it 652 over 222. It's better to find it in like this, so that maybe you can cross multiply. So we're just cross multiplying now. This multiply by this multiply by this, and then it's just gonna be we shift. There's that thing in physics where you can just shift like this. 2, 2, 3 over 652. So yeah, so we can be allowed to do that because it's gonna multiply, then multiply, and then after multiplying, this is gonna be divided. We divided by this. So you can use the long root or just shift. Let's find our answer. 223 over 652, and then our R is 3.409529. There it is there. And then this is our what? This is our R parallel. This is our R external. R external equals to R parallel plus R series. We are looking for our R series, which is R. And then we just come and substitute 3.43442623 equals to R parallel 3.4095292. We are just basically using this. And then we say plus R series, and then we just come and say, okay, what is our R series? Take this one that side and subtract. So now just gonna give us a 3 point, if we take this one that side, so which one is the total? That is the R external. So it's gonna be 3.442623 minus 3.40. Okay, let me correct. I made a mistake, a typing error. And then we continue to say 40920 it's a 95, it's a 9592 and 202. So our R is going to be 0.02. This is our R. So it's gonna be 0.02. Our R there is going to be 0.02 ohms. So there it is. Now when we continue, it's going to say how this is the question that we came here for. It says that how will this affect the reading of the ammeter A2? Choose increase, decrease, or stay the same. So they'll say now we have opened the switch. This is what we came here for. They say that now we have opened the switch. So now when they say now the switch is opened, how will this affect the reading on A2? So this one won't work now. This resistor won't work. Now if this resistor won't work, before we go to this one, or let me first finish this one and then we'll verify this one. We'll verify this one. I will just scan through the calculation that I just made, because I see that is 0.02. Sometimes you can usually find it unless it is an external resistance. But an easy way to verify is just to come and substitute in this equation. Come and substitute into this equation and see if you will get this EMF. So I'll show you how to verify your answer. So now it says that how will this affect the A2 reading? Choose increase, decrease, or stay the same. Give a reason for your answer. And then when you say give your reason to your answer, is to say that the ammeter reading is this one. So if we remove this, we'll have removed the resistors in parallel, as we have learnt in the previous questions. And removing resistors in parallel increases the total resistance. So this increases the total resistance. The resistance is inversely proportional to the current. Therefore, the current will decrease. So let me just put it in writing. Okay. I'll have to, let me first just verify before we go forward. So now the answer that we got is 0.02 ohms. Is 0.02 here. So this 0.02, it makes sense when it comes to this. Let me add 0.02. Yes, it makes sense when it comes to this here. But let me see. Let me go back to this one here. Let me go back to this one and see if that R external, to say that this side we come and say this 3. Here we come and say this 12 and 3,05. And then we come and say what? R external plus the R there. And then it's going to be what we call divided by this side divided by this. And then this goes that side. Wait. Oh, I see where I made the mistake. You see now, this is where the danger lies. As I said there, this one here, the procedure is correct, but this one, when it goes that side, it's gonna be minus 0.3. And then now, so it's gonna be 12 over 3.05 minus 0.3. So 3.6. So 3.6 here. 3,6. 3442623. There is just 3.6. So now the difference here is just, it's gonna say 3.6 here, 3.6, and then now here it's just gonna change, and then okay, let me just not write, but I was guessing, but it said minus 3.409 509202 0.22 ohms. So and then now let me just wrap here. So now I can wrap. What was keeping me from wrapping to do that one was that, okay, wait, I mismoved there. I mismoved this, then I'm wrapping this, delete, okay. Here it is. So now I have wrapped there. I have wrapped. So now we had said that if we remove this by opening the switch, the total resistance, when we remove resistors in parallel, total resistance R total increase. Therefore, it will lead to a series of events. The first series of events will be that the current decrease, I total decrease. So it ends there. It's decrease. So as I said that if they were asking about that one in the previous one, it will end here. Then they say that how will the brightness of the bulb L be affected? Choose increase, decrease, or stay the same. So this is the brightness of this bulb here. The brightness of this bulb. So now let's check the brightness of this bulb. So now it says that the information that you must use to explain is, before we say decrease, increase, we must first reason. The reason will lead us to the answer. So we start here. The total. So here, I had said they said how will this affect the reading of ammeter A2 here. So as I said in the ammeter A2 that the R total is going to increase, the IT is going to decrease here. So I had said decreased here. So that's our answer. So now this is 8.4. I wanted to start from here. R total increase, and then we come and say I total decrease. Let's continue. This is I total. Let's go to I across this resistor now. Now we are going to V internal, V lost, and V external. Let's check V external equals to EMF minus V internal. So now V internal equals to IR, which makes us that IR, which tells us that in this equation, if the current decreases, this one will also decrease because they are directly proportional, Ohm's law. So now you come and say in this, therefore the V lost decrease. Therefore V external increase. V external increase. And then if when the V external has increased, so now let's see about the voltage taken by this one. The voltage taken by this circuit this resistor is V equals to IR. It's gonna take some voltage. So because this current has decreased, it means that this one is going to take less voltage. So you will say the V R you only do this if like there is a resistor in parallel that takes the voltage before it goes to the, if there's a resistor in series that takes the voltage before it goes to the parallel VR. And then you just come and say, now you substitute this, or you just say through this equation V equals to IR. Therefore VR is going to do what? VR, we say decrease. And then therefore, if this one is taking more, is taking less, and then less voltage, and then we see that V lost is also decreased, it means that V external going to this one will be what? Will be higher. And power equals to, you'll continue here, power equals to V squared R. Therefore, this voltage here has increased now because this one is taking less and there is more V external. So therefore, the power will increase. So this is how we go into reason now. And then it says that, what is this? Okay, the letters A to F represent different qualities in a circuit as shown in the diagram below. And then it says that the internal resistance of the battery, okay, and then it says that write down the letters of the qualities which will be 0. Okay, they say switch S is opened, which S1 is open, S2 is closed, S2 is closed, S1 is opened, which is gonna be 0. Let's see now which are the qualities which are gonna be 0. Will there be voltage? Let's see. Current will not be able to flow through here. So the voltage across the battery is not 0 because it's gonna measure the EMF. If there is like, it's open, if it's open, if the switch is closed, it measured the V external. If the switch is open, it measures the EMF. It's not 0, this one. And then the internal resistance of the battery, there will be resistance in the battery. And then it says that current through the ammeter A1, it will be 0. Ammeter A1. And then when it continues, it says that current through A2, it is gonna be 0 because there is no complete circuit. A2. And then resistance of R, so let's check this one, potential difference across the 9 ohm resistance. So potential difference across the 9 ohm resistance. So this one, okay, so it's just this of the whole circuit. So let's see if this one will work. These two also won't work. And then we say A1 and A2, we had said, and then the resistance of R and also the potential difference. So also E and F, they will be 0 because what are they measuring? The resistance of R, resistor R, resistance of R, the potential difference. Okay, but the resistance of R, it will still have its own resistance, but what we know that the F, the potential difference across, you can find potential difference with current, but the resistance will still be there. So that will be the end of our live stream. So if you learned something, be sure to like, subscribe. So we'll continue with this. Today I'm just a little bit tired. I had prepared for us to go through this, but we can go through it, but only consider this one only, because this is what we want to do, the long questions of the electric circuit. So let's see this long question. Both switches are closed, these switches. And then how will the reading on the ammeter A1 be affected? Choose increased degrees of steady. So let's reason. So this one is a funny circuit. but you must know that these branches are like they are connected in parallel to one another. It's like adding more resistors in parallel. So you have never seen this. It's okay. Let me say you have never. It's rare to find a circuit like this in question papers, but if we get it, can see that no, these branches are in parallel to one another. So if we close, which switch are we closing now, or we are closing this one, and then this one was closed, and then what do we take of this? When we close this one, we now add more resistors in parallel. When we add more resistors in parallel, R total decreases. Before you get to an answer, these are your reasoning. And then you say I total increase. There it is. I total increase. Therefore, V lost increase. V loss is always directly proportional to current. V equals to IR. So if this one increases, this one will increase. Therefore, if there is more V lost, it means that there is less. If there is more V lost, it means that there is less V external. So it means that because EMF is constant, this one there will be less taken from this, and then you come and say EMF is constant. There are points that you don't leave out. It's always there, this one. And then you come and say that now, therefore, because V lost has what? Has increased, V external decreases. V external decrease. Therefore, now the reading on what? On A1, they will say that if you close, what will be the reading on A1? The reading of A1 is going to do what? Decrease. How is it? So we see the reasoning that if now there was this battery was now supplying only this circuit, now it's going to supply the other circuit. So we see that there's another branch that has opened that side, that we see that the current going through there and going through there, they are not going to be the same. But if they were looking for the current here, we were just gonna use this, but that's not the current over the whole circuit. Is A1. If they were asking of the current over across the whole circuit, which is here, we are going to end there where we say current increase. But now we are looking over the current across this. Now there is an additional branch here. Because there is an additional branch, it means that this one was the total current. Now the current is going to be split to go that side also. So now there's a split of current. So this is our end of the stream. So this is always the way that you reason. So you must follow this reason, and then you'll get your answers. Thank you for staying along.